Hi everybody. Well, I did it again. This is something I'm going to have to learn to deal with on this camera. When you push the record button, there's a tiny little beep, and when you push the record button to stop recording, you get two beeps. And there is a tiny little indicator on the screen, if you look at it, to tell you if you're recording or not. But other than that, you really don't know if you're recording or not. And what happens is, if you push the record button too quickly, it turns on and off immediately. So now you're backwards. So every time you push the button, you're turning the recording off, and every time you push it again to turn it on, or turn it off, you're actually turning it on. So I got about an hour of footage of me moving things around. Then it shuts off when I do the part that I wanted to record. Then it comes back on when I move things around again. This is about the third video that this has happened on. It's really, really annoying on this camera. And if I'm really engrossed in what I'm doing and I don't look at the screen specifically and pay attention, it's easy to miss. So we missed about an hour of footage here. But most of the important stuff I did get, and from the last portion of the video, so this is a good thing. And what we're going to do in this video, I know I promised you in part one that we would do a solder and talk, and we were going to modify the other channel. I since have changed my mind on that, because what I wanted to do real quick was just compare the two channels and then go ahead, and I was just going to do like a 5-minute clip of that and then go through and finish the mod. But I ran into some problems, some very serious ones, which led me down the rabbit hole. Not confusing the rabbit hole, but just, I need to do this, that, and the other thing. You know, there's a hole in the bucket, dear Liza, one of those things. So we ended up doing a little bit different direction on this video. Where we went with this was, we did the bias circuit for the output tubes, and we did a modification on the negative feedback. So those are the two things you're going to see in this video. In the midst of it, I also checked the front end of the amplifier, the volume control, the tone control section, and so forth, and found a whole myriad of problems, including the potentiometers had all been embalmed with that red deoxit embalming fluid, as I call it. I tried using, regular cleaner to clean out most of that oily substance, but ended up having to disassemble all of the pots and clean them correctly, lubricate them correctly, and then reassemble them. And I was able to bring them back, so they work. That's going to be a separate video that I may or may not post, because I kind of did a few little rants in there, but let me know if you're interested in seeing it. I think it might be interesting, but we'll see. This video, though, we're going to focus on those two things, the bias supply and the negative feedback. So if that sounds interesting, stay tuned, and we're going to really just kind of cut right into the middle of the video. And again, it's the most important part of the video, so luckily we got that part on video. All right, here we go. Now I have a plan to improve the bias circuit. More about that in a little bit. But right here is the bias circuit in its current form. And if we look at our schematic, we've been doing a lot of schematic looking, haven't we? If I make it right side up. So here is what we have right now. And it's pretty simple. You have a 23 volt winding on the transformer. You have a bridge rectifier, and they're taking the positive and they're running it to, it's going to the chassis ground, and then the negative, so it is a negative power supply. Flip this pair of filaments over down here, and you can see that the filament string is just being put across this negative power supply. And they're saying that it's about negative 22.5 volts after it goes through this 15 ohm resistor. Then they're also going into this little voltage divider, and that's what's picking off the voltage for your bias circuit. You can see it goes into here and into here. So we're going to change that up a little bit. And like I said, more about that in a little bit. But right now what I'm concerned about is SR1, because I believe that is part of our problem. This is a selenium rectifier, that's why it's called SR1. Selenium rectifiers have a higher voltage drop typically than a silicon diode. So we'll have to see what this comes out to. Typically when you full wave rectify a transformer winding like this, the unloaded voltage is going to be about 1.414 of the RMS voltage of the transformer. So for instance, and that's if you don't draw any current. In other words, just the open circuit voltage there, you would take 23 volts times 1.414, and you're going to see about 32.5 volts there through your regular rectifier here. It'll be a little bit less than that, but it'll be in that 30 to 32 volt range. And then we will have to take that into account, because once we put the loading down on it, of the current of these filaments, we're going to look those up. Then we have to determine, we'll probably have to change this 15 ohm resistor to something else. And the other thing we need to get rid of is this 1000 microfarad capacitor. That's this guy right here, and if you noticed, it's in a cardboard case and it's isolated from chassis because this is a positive ground or a negative power supply. So what we put in here, we'll have to make sure it's also isolated. I could get another one of these, and an original one, or I could restuff this one, but I may decide to just put a conventional capacitor in there. We'll see. This bridge rectifier, the selenium bridge rectifier right here, we're going to remove, and it only has one mounting screw, which is right here, and I am going to replace it with this rectifier. And you can see it's about the same thickness, but the terminals stick out pretty far. I have plenty of room in here to do that underneath. However, we just have to make sure that this shielded tubing for the power line that's going up here will not come in contact with this. And I think we'll be okay with that. Here's our 15 ohm resistor. That's one of those ceramic resistors. It's a 5 watt. But we're going to, again, we'll do the calculations to see what that resistor is going to need to be. So that's where we are. After we do that, then I'll show you what I've come up with for everything from here out, so that we can do something about our bias circuit. And I'll explain why I'm doing it the way I am and so forth as we get there. So let's get started. So working on this bias circuit here, my unbiased opinion is that this bias circuit sucks. So we're fixing that. But in the meantime, I had to get this capacitor out of the way and look at a few other things, and I noticed these diodes were getting pretty crusty. You can see the ends of them are kind of getting bad. These leads are very tarnished, and I'm just going to replace them with a set of really good ON Semiconductor 1N5408s. That'll take care of those way better than the ones that are coming out. In addition, we'll get rid of these little film capacitor, or these paper capacitors, and replace them with proper safety caps. I ordered a capacitor change-out kit for this. They actually make a drop-in replacement set of these for the 800Bs, and they're all original, you know, the right values and so forth. But just doing some quick check with the capacitor wizard, just ESR. This one that's kind of leaky looking is actually in not too bad a shape. This one here is not too bad either. You can see both of those elements. This one over here, starting to get tired, but again, acceptable that it will work. This one over here, however, all three elements are totally open. You can see. Now here's the strange thing. If I go from one capacitor to the other, I get a reading, and it's not too bad of a reading either. So what happens when I get a reading from one end of, when I get no reading from any of the capacitors to the common, but I do get a reading from the capacitor to capacitor positive? Well, what that's telling me is that the connection inside the can from the common lead to the three capacitors in there has broken or has corroded or has failed. So these capacitors, they do have capacitance with respect to one another, even though they're out of polarity from one another, but none of them have capacity with respect to ground. So this whole section of three caps is pretty much like it's non-existent, and that makes a lot of sense, because that explains why, if I zoom in, this resistor here is cooked, and when I try to measure it, it is way off. If I recall correctly, it is not 1.2K at all. If I back up here, let's back this way up. It is not 1.2K. Let's see if we can get you in frame here. It's 204 ohms. It's really cooked. And so that explains, this power supply has a lot of issues. The front part of it that we were using when we were doing our testing was fine. But when you get down the road here to the supply for the tuner and for the preamp section and all that, definitely we have problems. So that'll eventually get replaced. I'm going to rebuild this whole thing here, but right now we're going to just focus on the bias supply, because again, I have high voltage from here to the tubes, so I can continue to test the amplifier section. We just can't test the preamp or anything, because none of that's going to work, and in fact it does not. If you try to pass a signal through these tubes in the front, they don't work properly. Like up here where the tone control section, none of that works right. All the voltages are kind of strange, and just the signal won't go through. And the other thing was, these potentiometers have been serviced by an undertaker, I am sad to say, and they have been embalmed with, you know, this embalming solution. Soaking them with 14 gallons of red deoxit will not help a scratchy carbon potentiometer. So I'm going to clean them and take them apart and fix them the right way, but yeah. That's later though. We don't need any of that to test this. I just need to get the bias supply working and make sure that the front part of the high voltage supply is working so that I can finish my tests over here. Okay, before we do the big reveal here, let's review where we came from, so then we can see where we're going. Again, we have this 23 volt winding on the power transformer. It goes through a selenium rectifier. The selenium rectifier has quite a bit of voltage drop on it. So if you used a regular silicon bridge rectifier, a modern one, your voltage here, your unloaded voltage with no current drawing on there, will be about 1.414 times the RMS voltage right there. which is 23 volts according to this, right? So we hit that, and we should have somewhere around 32.5 volts. And it's going to be a little bit less than that. Then, depending on how much current you draw here, that will drop a little bit more. So it's probably going to be somewhere around 30 volts right there. Now they're saying that there is negative 22.5 volts. And again, we have this 15 volt or 15 ohm dropping resistor. There's like a little pi network here to make this a quiet power supply. And then they ground it after the 15 ohm resistor. It then goes through this little voltage divider, which gives you a fixed voltage of negative 14.7 volts for your bias. And you can see that down here where they're telling you on each tube that's what you should have. That right there in and of itself is a big problem, because with the elevated mains voltages today, instead of 110 to 117 volts, we now have as much as 125 or 126 volts. So our B plus voltage is going to be higher than that 393 volts, which is going to throw this all off, which is going to make your bias need to be different. This is a problem with this amplifier if you leave it stock. So here's a data sheet for the 7591 output tube, and if we look at some of the settings, we're interested in this column, this set right here, not because we're using fixed bias. That's what that bias voltage is. And you look, if you put on the plate supply voltage, if you have about 400 volts, and we're going to have somewhere between 400 and 415 volts there, you need negative 16 volts on your grid. That's your bias voltage right there. And you can see there's not a big jump in bias voltage between 400 and 450 volts. But if you go to 450 volts and then you put a high screen voltage, then you really need a lot of this. So the screen voltage also affects all of this. Bottom line is that 14 volts is way down here somewhere. If you only had like 320 volts or 330 volts, we'd be okay. But as it is, we don't. So we have to fix that. And really, ultimately, we don't want to keep playing around with these resistors here to make it into, to try to get it into what voltage we want. We want to be able to adjust this. Now, traditionally, people would put a potentiometer somewhere inside here. Like they would split this and turn it into maybe a 4.7K resistor and maybe put a 5K potentiometer in series with it, and then you could adjust that to change this voltage a little bit. I don't like that. I like to be able to adjust it. In addition, sometimes people will put a adjustment like a splitter potentiometer to be able to vary the bias between the two tubes. So if you have an unmatched pair of tubes, you can match them. Now, I don't like that, and I typically will not put that into my amplifiers, especially if it's hi-fi versus a guitar amplifier. Because really, if the tubes are not matched and you force them to be biased the same way when they start, since they have different mutual transconductance, as you drive a signal into them, they're going to drift further and further apart, even though at idle they're balanced. So I do not put a balancing pot in any of my designs, and I make sure that I use matched tubes, or at least close match. It doesn't have to be perfect match, but at least somewhat close. And then if they're a little different, I let them be different. It doesn't matter. It's the same difference as if you tried to balance them before you drive a signal into it. So anyway, we're going to put adjustable bias for both of these. And I would like to have an individual bias adjustment for the right channel and an individual bias adjustment for the left channel. That takes care of that problem. But if you notice here, you have these four tubes, V10, 11, 12, and 13. And that is these tubes right here. So if you look, you have V10, V11, this is your phono stage. Then you have V12 and V13, which is your line, your tone control and line stage. So this is where all the small signals are going to be in the amplifier. So they put the filaments at DC, so they're putting a DC voltage. That's a great idea to keep it quiet and keep hum out of the tubes. But the problem is, again, if we have different mains voltage, this is going to drift around and this voltage could change. Messing around with these could also change your bias voltage, because more and less load on there will change that. Now a tube is a pretty constant current load, but nevertheless it all affects it. So I would like to have some sort of a way to separate this and regulate it so that we have a constant 24 volts roughly on these filaments. They're putting 22.5, which if you split between these two, that's only going to give you about 11.25 volts per tube, which is fine. I mean, you don't need the full 12 volts. But if we put 12 volts on it, it won't hurt it either. Anyway, that's where we're at. Now let me show you what I'm going to propose that we do to change all this and fix it. Okay, here's the schematic I made up of the changes that we're going to make, and it's a very, very simple circuit. What we're going to use, what's really going to be the heart and soul of this whole thing, is, I'll show you here if I can get one out. Let me see. Right there. This is an LM337T. And what that is this is a linear adjustable negative voltage regulator. So there's a lot of circuitry in this little chip, believe it or not. It has over current protection, it has over temperature protection. So it can actually crowbar the circuit down and shut it off if it overheats or you draw excessive current. So it's pretty well protected. It's good for about 1.5 amps, and each of those filament strings draws 150 milliamps. So if you put the two filament strings in series, like what we were seeing right here, that's going to equal 300 milliamps of current through that set of filaments. So 300 milliamps is way less than 1.5 amps. But we will make sure that we mount this on the chassis to kind of dissipate some of the heat, what little bit there is. And I'm going to use 3 of them. I'm going to use one of them with a fixed resistance here, the voltage divider, and this is going to set that to somewhere around 24 or 24.5 volts. And this is going to go to that filament string and feed them. Okay, I'm removing the old selenium rectifier and replacing it with a silicon modern bridge rectifier, a very heavy one that will not ever have any problem. So that's there. Very simple. We're going up from a 1000 microfarad capacitor, because we don't have the Pi network anymore, to a 2200 microfarad capacitor. And that'll be just fine for this circuit. It won't hurt the coil or the transformer winding or anything like that. It'll be just fine. And it's a pretty low ESR. It's a good quality capacitor we're going to use. Then we're going to go into each of our regulators. We're just going to have 3 of these guys stacked in parallel. As you can see, they're all feeding off of this line here, and then they each have their own separate output. And like I said, this one is just fixed at a set voltage. The other 2 are the same circuit as this, except where you would have this 2.2K resistor, we have a potentiometer, a little trimmer pot, a 15-turn pot or 10-turn pot, that'll be 2K. And you can see each one of those, and those will be your left and right bias. And of course there's the outputs for left and right channel. So the left one will go over to here, to this bias tap right here for your outputs, and the right one will go down here to this one, same thing. So we're breaking these apart, and we're going to have two separate adjustments. A lot more traditional to what you're used to seeing. Now, after we implement all of this, we have to check a few components. If you remember, they put little 10 ohm resistors, and they were pretty tiny. And I know I've shown this many times, but these tubes were very badly heat damaged, and there was excessive current because of the incorrect bias. So we don't know what kind of damage we did to those fusible resistors. They may have changed in value. So we're going to check those, replace them if necessary. Then we're going to go in and we're going to measure our bias, which is, we should see somewhere around your zero signal plate current should be somewhere around 85 milliamps, and that is for two tubes. So each individual tube should read about 40 milliamps, about 42 to 45 milliamps, something like that. Okay, so we're looking at about 40 to 42 milliamps across that diode. Now, a little word of warning. This is the plate current they're talking about, okay? We're measuring, by putting that resistor here, we're measuring it at the cathode. Cathode current, believe it or not, is not the same as the plate current, because the cathode current is going to also be influenced by the screen grid current. Now, this screen current is very low. Typically, your screen grid has only a few milliamps, so most people ignore it and just measure this and treat it the same as if it is the anode or plate current. And that's perfectly okay to do that, but just understand your numbers are a little bit different than if you go and do the traditional measuring the voltage drop and doing the math and measuring the actual plate current. Either way, it doesn't matter. So that's what we're going to do. We're going to check that, and then we're going to make the final adjustment. It's probably going to be this, or it might be a little higher than this. We'll see. Depends on how the tubes are working. After that's all done, we should be able to drive a signal into our preamp circuit that we already modified. One side's modified, one side is not, and we're going to compare the two and see how they perform. And remember, I did not change the feedback on the modified one, so I won't be surprised if something is going to need adjusted there. Okay? All right, let me give you the reveal now. And here it is, our modification. Starting here at the main power, the fuse socket was cracked really bad and it was ready to break, so I had to put another fuse holder in there. No big deal. I got rid of these paper caps and I put proper safety caps in here. So I have this one right here, and I have the other one right here. You can see where it went. This one used to go from here over to this, from here over to this ground lug right here, so I disconnected it, and I'm just using the ground lug that's right down here. I got rid of these older diodes, and I just replaced them with a modern set of 1N5408s. They're a 3 amp diode. They're good for 1,000 volts. We're never going to have a problem with those. The selenium bridge rectifier, which is this one here, and you see these all the time on old tube gear. I removed that because I think one of the diodes in here was bad, if you recall, as was one of the capacitors. So this capacitor is also gone. Our 2200 microfarad is right here, and you can just see with this antenna in the way, this little antenna wire, the new bridge rectifier is just, I used the existing mounting hole and it's mounted in the same place where the selenium was originally. So the selenium one was down in there. Now this is down in there. I don't know if you could see it. Okay. These two resistors here, those are these two resistors right here. And this right here is this down here, and you can see it's up on a sill pad. and I have it isolated electrically from the chassis because this tab is actually connected to this. So we don't want that. And then we have the ground, and we have input and output. And here our input is in the middle. You can see it goes over to the bridge. And then we can see the center of these two going to the adjust pin. And then you have your output right here going to this green filament string wire. So those are the changes we made on this side over here. Pretty straightforward, and everything fit right in there. And I used an existing hole here, so I didn't have to drill anything. So if somebody wanted to tear all this out and put original parts back in, they could. Now right here is where things get kind of interesting. I used a little piece of proto board that I had, and I made up these two bias regulators right here. So what you see here, these components, these little film caps, the two regulators and the resistors and pots are all right here, and there's one extra capacitor. And the reason you need that is if your feed line, which is this green wire, is longer than 3 inches away from the bridge rectifier, which it is. This is probably about a 12-inch run of wire. They want you to put a 1 microfarad capacitor at the inputs of these, which is what I did, just to help with stability. Other than that, that's the circuit, and it works perfectly. Works perfectly. So you can see our modified side and our unmodified side. And you can see the yellow wire goes to this side, the orange wire goes to this side, and it feeds your 330K resistors, which feeds our two channels. And if you measure right there when you turn the power on, you'll see that we actually have our bias voltage now, and everything works. So if we go here, I turn this on, and we go from ground to one of these input pins, and I turn this on. Hopefully it's not going to blow up. And you can see I have it set to 16 volts right now. And then all we need to do to adjust it would be, and I do have tubes in it right now, so I'm not going to leave it on very long because it gets hot with it upside down like that. But you can see I can adjust this wherever I want. There you go. So that's that. And if I look at my filaments, you see here, 12.6 volts right on the money. And that's what's going on to each of those 12 volt filaments of the 12AX7s. Now before we can do anything to adjust our bias, we have to check those cathode resistors that were installed by the previous owner. So we have it set to ohms, and we're going to look at each resistor. They are 10 ohm resistors is what they're supposed to be. So you can see that one's right on 10 ohms, which is good. That one's 10 ohms. Very good. That one's 11.8, and that's not good. Well, maybe I'm not making good contact. Hold on. Nope, that's 10 ohms. Sometimes there's a little bit of tarnish on these leads. 10 ohms. Okay. So we can safely say that when we use these to measure the bias current, then it'll be fairly accurate. And in order to measure the current, I equals V over R, okay, or E over R. So you take the voltage that you measure across that resistor, and you divide it by 10 ohms or by 10, and that tells you directly how many amps of current, or milliamps in this case, that you're going to get. So for instance, if we read a half a volt across there, let's say we get 500 millivolts. 0.5 divided by 10, that's going to be 50 millivolts, and that's going to be way too high because, like it said, we want it to only be around 40 millivolts. So we would need to lower that voltage a little bit, or we would have to crank our bias a little harder till we get that where we want it. We don't know where that's going to be yet until we do the adjustment. So we have the tubes fitted in there, and we want to set our bias, and I'm just going to do a preliminary. I'm going to kind of set it cool right now. And again, we looked at our chart, and if you remember, at 400 volts right here, push pull class AB, at 400 volts we want somewhere around, here we go, we want the zero signal plate current to be 85 milliamps for 2 tubes, and half of that would be 42.5 milliamps. So I'm going to run 40 milliamps per tube. And if you recall, we are measuring at the cathode resistor, at that 10 ohm cathode resistor, and you can see I'm connected across it right here. And so really, when you're looking at the cathode, you're looking at the anode plus screen grid current together, so it's going to be a little bit off, but again, we're not going to worry about that. We are going to set the cathode to 40 milliamps, which is a little bit low. And then once we get everything dialed in and working with the rest of the amp, then we'll turn it up a little bit to the proper current. But it should work just fine without any crossover distortion with this, or worst case scenario, a tiny little bit of crossover distortion. We'll see. So let's turn, first of all, I had to put the filter on the lens, and watch me forget to take it back off. But you can see what the filter does. As I rotate it, see what it does to that screen there? So this actually helps me to get rid of the glare, so we can see on the camera. We can see these numbers a little more clearly without having to see the glare. Okay, power on. And I have 125 volts full power going into the amplifier right now. And this should be, well, what should it be? Well, across a 10 ohm resistor, E equals IR, so the voltage would be the milliamps that we want, which would be 40 milliamps, so 0.04 times that 10 ohms, and that's 400, you can see 400 millivolts. So if we put 400 millivolts across that resistor, and you can see it's hot right now, then we should have our proper bias that we want, our 40 milliamps. So let's turn this right now. I'm going to adjust it, and we're going to turn it until it's 400 millivolts. And just like that, we dial it right in. See, this is the beauty of being able to, and there's 400. See, that fixed bias that was in there just was no good for what we're doing now, because the new vacuum tubes today are not the same. You know, the valves that they make today, even though they say, you know, 7591, they're not the same as the old Westinghouse and RCA and GE and so forth, tongue saw of the old days. So you can see this one's really hot, 600. So that's almost 60 milliamps. So let's turn this one down. Hope you're seeing what I'm doing. And again, we're just roughing this in right now. Okay, good enough. And now we know we're just not going to be running the tubes really hard. So that'll be just fine. Okay, we're ready to do some preliminary tests. So let me get set up for that, and then I'll explain what we're going to look for. And just so you know, here's the other tube in the pair. I just want to show you, I am comparing them, but this is supposedly an Apex matched tube set. But that doesn't mean that the same bias voltage will give you the same bias. Little tiny differences in your resistors and so forth could make a little difference, but really this is not as much as you think. This is 375, 376 milliamps versus 400 milliamps on the other, or millivolts. You are talking a difference of a half a milliamp, so, or 1 milliamp. It's not a huge difference. You know, you're only off by a little bit. So really, believe it or not, these are very closely matched tubes. Really, where you would see a big difference is if this was like 200 millivolts, which would be, you know, 20 milliamps, and the other was 400, which would be, you know, big difference. So think of it as 37 milliamps or 38 milliamps versus 40 milliamps. Not much difference. Okay, we have the signal generator connected up through two coupling caps into the two left and right channels. And where we're feeding our signal is in the preamp section, or the driver section. We're feeding it right here into this point right here onto pin 7. So I'm just clipping right onto this side of this 47K resistor on each channel. And they're just both tied together. So we're putting exactly the same amplitude of signal into the amplifier. And I'm driving about 1.2 volts RMS through these caps. And even though they're shaped different, they are the same value film caps. They're both 0.1 microfarad capacitors. Now, let's get over to the oscilloscope and let's take a look at what happens. We're going to drive the signal into it, and what you're looking at the scope is the output of the speaker terminals through an 8 ohm resistive load. So we're just running it into the dummy load. Alright, power on. The yellow channel that you're looking at is the modified channel. That's the channel that we put that we changed the components on. The blue channel is the unmodified one. And you can see where, because of the different, I'm still using the original feedback resistor and capacitor, you can see that I have a greatly reduced power level. Alright? But you can see both channels look pretty daggone clean. And if we drive the amplitude up, we can drive it up into clipping. Right there's clipping of the blue channel. There's just below clipping a little bit. It looks pretty good. Now, here's the thing. We're going to leave that on there at the moment, and we're going to look at the output right now of, let's see here. Let's first look at the output of the unmodified channel. Okay, so this is the unmodified channel. There you go. And that's pretty good, I think. And if we move over to the other channel, a little bit higher. Okay, so we definitely have to make some changes. I'm sorry, strike that, I have it backwards. That is the unmodified channel right there. So you can see I have this all confused. There's my breakout box. these two here, one's going to the blue, this is the blue channel of the scope, and this is the, so blue channel of the scope, and this goes to the distortion meter, and then this is the yellow channel over here. So yeah, so right now this is the unmodified channel, 500 and little, about, well, you see it. And if we move over to the one that I did the mod on, there you go. Now, what I'm going to do is, it's an unfair test because the blue channel has a higher output right now, and that's why you're seeing the higher distortion. So what I want to do is I'm going to disconnect the unmodified channel because I don't want to drive it really hard into clipping. Just like that. Okay, so now it's disconnected. And I am going to drive the amplitude of this modified channel up to the same level. So we're measuring them at the same thing. So right there's your clipping, roughly. Somewhere around there. And if we go here, this is very unscientific. It's about the same. It's within 0.1%. And you can look, and we are actually putting out 28.57 or 28.6 watts per channel, or at least into this channel right now. So this thing's doing its 28 watts, which is what it should do. And what we're going to do now is we're going to try to adjust that feedback resistor to make both channels kind of match a little bit, so we know what it needs to be. All right, so let me get set up for that. So far, this is working great. I have my resistor decade box, and this is going to make it easier to work with different feedback resistors. I've removed the little 3.9K resistor that was in there, and I just kind of clipped my decade box across where that was. We're going to come back over here, and I have both channels connected once again, so we can, ooh, that's crooked, isn't it? So that we can once again see what we've got. Okay. All right, good enough. Let's turn this on. And I've moved that resistance to 4.7K. Let's see what happens. And you can see it's still not good enough yet. So we're going to just step through . Alright, that got them almost perfectly on top of one another. As a matter of fact, if we move these, you can see they are perfectly lined up. Alright, that's good. So now both channels are, let's make sure they track all the way, and they do. Look at that, all the way up and down. See if they both clip together. Actually, we get a little bit more softer clipping out of the modified channel. See, the blue channel starts to go, but you get a little bit of, tiny bit of ringing, and that's because we didn't change that capacitor yet, right? So there we go. So right there, look at that. We are now getting, okay, back to 28 watts per channel, 28.6 watts. And we are getting over 1% total harmonic distortion now. But that, as you could see at the bottom, I don't know if you can see on our modified channel, getting a little bit of fuzz down there. And that's some ringing, and that's because we need to change the capacitor now. We need a little bit different capacitor. So let's check and try a couple different versions of those as well. Okay, I now removed this 330 picofarad capacitor that was in parallel with the 3.9K, and I reduced its value to 250 picofarads. So I went from 330 to a 250. Now, you would think that won't make a big difference, but we were getting 2.8% THD with the 330 picofarad. Let's turn this on now. You can see that ringing by and large is gone, and we do have a little tiny bit more amplitude than the blue channel, which is okay. But more importantly, 29.3 watts, so it's actually now higher power than it was before by a little bit. And look what happened to our distortion. 0.3. Now, a lot of you folks that are used to watching my videos on the solid state amplifiers, I know what you're saying, that's really high distortion, but on vacuum tube amplifiers it is not. That's actually not a bad thing. Let's take a look on the spectrum analyzer and see just what that looks like. Before we do that, let me move the meter over to the other channel so that we can see how they compare. And you can see it's double. It's 0.6 instead of 0.3. So actually our modified channel is performing slightly better. Now, can you hear all this? Very debatable. Some can, some can't, and also it's the type of distortion. So let me get connected up to the spectrum analyzer. Okay, I have not changed anything on the settings of the amplifier from when we were just looking at the THD meter. So let's see what this looks like. Now, first of all, we are on the modified channel, the one that I made the changes to, okay? So here we go. And you can see right there is your fundamental, and here's all your harmonics. And look, there are odd and even harmonics. See, when you look at these little transistor amplifiers, you normally only see the even harmonics. But one of the characteristics of vacuum tubes is the odd harmonics as well. And you can see this is actually pretty low, believe it or not, for vacuum tubes. Now let's move it over to the other channel. And I'm going to just leave everything running, so as I move the cord over, here we go. This is the unmodified channel. And you can see it's considerably higher. So you see the difference? They're still pretty comparable. I mean, this has more distortion, but it's still not bad. And again, I'm driving this thing almost to clipping. It is really driving hard. And if we turn this down a good bit, you can see it starts to level out. So there, once again, is our unmodified, and you see here's your odd harmonic, there's your even harmonic, and then another odd. And that is the unmodified channel. If we go over to the modified channel, let's see what it does. Let's let it settle. You can see it actually has a little bit different characteristic. It actually has a little bit more of an odd harmonic at the lower volume. Now what that tells me is that we still have a little bit too much capacitance on there. So what I'm going to try now is I'm going to reduce that capacitor from a 250 picofarad to somewhere around maybe a 200 or a 150, and we're going to see the difference. Okay, I've now taken the 250 picofarad capacitor out and replaced it with a 150 picofarad. The amp is turned on and warmed up. Let's turn it on and see. If you remember, we had a odd harmonic, even, you know, and then it kind of stepped down and disappeared. But it actually was a little bit more distortion than the other channel. So now let's turn it on and see what it does. See if we get any difference. There, and look at that. Pretty much wiped it totally out. So now all we have is this tiny little bump here of an odd harmonic. Now, you might say it's perfect, but we're still not out of the woods yet. And the reason I say that is this can also be, we can still have problems at high frequency. So now what we're going to do is I'm going to move the frequency up to 10 kilohertz, like this. And there's our fundamental. And if you look at that, it's pretty daggone good. There looks like there's a little tiny over here at, let's see, 12, 14, 16, 18, right at 20 kilohertz, there's the tiniest little bit of distortion, but hardly anything. And if I go to, I'll go to 19 kilohertz so it stays on the scale. And there's our 19 kilohertz fundamental. There is no distortion at all. And looking at the waveform, it's tracking perfectly with the other channel. All right, let's now compare to our other channel. We're going to move this over to the unmodified channel, and we're still at 19 kilohertz. And it looks good too. Excellent. And if we go to 10 kilohertz, wait till it sweeps through and cleans up. And you can see, same thing. Very good. So we're not having any problems with that. And by the way, we're running at about 17 watts right now per channel. So it's not at full power near clipping. I would say this amp is ready to go. I mean, this is where it needs to be. Okay, we have one last problem here, and I want to show it to you. And what I'm going to do is we're going to put a 1 kilohertz signal at 1 volt RMS into the unit. And if I hit output, you can see we have a pretty good solid signal. And if you look at the amplitude of the signal, it is about 1, 2, 3, about 3, almost 3.5 gradicules tall. You see that? See where I'm counting? So it's 1, 2, 3, and just about a half gradicules. Now if I go to 20 hertz and I move my sweep down, you can see both channels have a huge drop off on the low frequency with the same drive signal going in. So I'm going to fix that. So let me shut this off, and I'm going to do something right here. And we're going to see what we can do here. And look at that. At 20 hertz, we are much closer now. We are 1, 2, just right at 3. So just a little bit under the amplitude of 1 kilohertz. And if I go up to about 40 hertz, or 50 hertz, my amplitude is the same as 1 kilohertz. So I only have a little bit of drop off between 50 and 20 hertz. And if you notice, the unmodified channel has a huge amount of drop off. The signal is clean, but it has a lot of attenuation. So what did I do to fix it? Well, what I did was I added these capacitors in parallel in series with the feedback loop. So if you look right here, here's your feedback. Okay, and remember on our modified channel, this is 8.2K, this is 150 picofarads. I broke this line right here and I put essentially about a 0.75 to 0.8 microfarad capacitor right in line with this feedback. Now what does that do? Well, it acts like a high-pass filter. And what that's doing is the higher frequencies can pass through here and provide feedback to the circuit. The lower frequencies get attenuated by that capacitor. So what that means is we get less feedback signal at low frequencies than we do at high frequencies. So it's kind of doing the opposite of what this capacitor is doing. This capacitor at high frequencies bypasses this resistor right here. And again, you could play with those again, but and we could technically put a big capacitor there and put a different capacitor here, but as it is, it works this way. So there you have it. Okay, another concern would be phase shift and everything with those capacitors being in there like that. And as you can see, there is a little bit of phase shift, but it is pretty linear. The only time it really starts to get ridiculous is at the extreme ends, of the frequency range, and we're starting to see limits of the transformer and the circuit itself and all these things. But really, when you look at it, the actual gain across the board, we're actually getting a little bit of extra gain at the low end now, and it's staying pretty flat at the high end. So we could probably reduce that capacitor a little bit more, or increase the capacitor a little bit more, and it would drop that down, but that's pretty close. That's not bad, and I bet you this amp is going to have a real warm, mellow kind of sound to it. So I like it the way it is, and I think I'm going to leave it that way. Now once again, there is probably a combination of resistor and capacitor in series here for this right here that we could possibly get it to track pretty close to this without having that series cap in there, that 0.78 or 0.8 microfarad. But I'm not really sure that would affect some other things possibly. The way this is working now, I'm not getting any kind of ringing. I'm not getting any kind of problems like that. It's looking really good. I think I'm going to leave it. Everything is how I would expect it to be. And without that 0.8 microfarad capacitor in series, this is what it looks like. You can see it's a little bit flatter in this area, but there's a huge drop off at about 100 hertz. You could see it just kind of drops down about 5 dB. And the phase shift is all over the place. You see it at low frequencies. You're way off scale there. I mean, I would actually have to scale this there at 45 degrees. So you're almost 90 degrees off phase here, and you could see it's dropping, I don't know, somewhere around 35 degrees or so. So your phase shift is all over the place. So again, if we put this capacitor back in the way it was, and let me get it fixed in here. There. And we run it again. I think it's looking a lot better. Okay, and if I go and I scale this one the same way so they look the same, there we go, and we go to 45 degrees, you can see how much more linear it is, really. I mean, it's so much better. So there you go. We're going to leave it alone. Okay, with both channels, here's a square wave. And you can see it's pretty nice. Has a little bit of slope to it, but that's okay. And then if I add a 1 microfarad capacitor to the load of the modified channel, which is the yellow channel, you can see there's absolutely no ringing, nothing whatsoever. Okay, there is our left channel completed. All put together and performing probably better than it ever could. Now here's the thing, we could make a few minor changes to the existing design of the other channel, but we would not have the problem, we would not be able to solve the problem of the elevated voltages between cathode and filament and cathode and grid. So those issues would still exist, and we still would have the little bit greater distortion. So I think it was well worth making this modification on here, if you have the means to do it. So there you go. Now, I know I promised in this video we were going to do a soldering talk on this other channel, but I really had to make sure that everything was going to work properly and was finished before we did the other channel. Now it's going to be so much easier to do the other channel. So that's what we'll do in the next video. And as always, I wish you all peace, joy, happiness, and good health. And I really hope you enjoyed this video. This was fascinating to me. I learned an awful lot from this. And I hope you learned a few things as well. Until next time, stay well and take care. Bye-bye.